Greetings, YouTube. Beautiful mind here. We have question. This serves as the first question in a series of three for calculus. And so let's see. It says for each of the numbers a, b, c, d, r, and s, state whether the function whose graph is shown has an absolute maximum or minimum, a local maximum or minimum, or neither a maximum nor a minimum. Right. So in this context, the simplest way I can sum it up, maximums are basically the peaks of mountains, and minimums are the bottom of valleys. And so in calculus, we're always studying graphs and curves. And so again, the local max is going to be, when you have your curve, again, the peak of the mountain, the local minimum is going to be the bottom of a valley. And the only distinction between local max, the local extrema versus the absolute extrema, with the absolute max or absolute min, you have to compare your peaks and valleys to also your endpoints. All right, so you can only talk about absolute max or absolute min when you're given some definitive endpoints. Yeah, so, okay. So with that in mind, let's see. 1, 2, 3, 4, 5, 6. Okay. Well, okay. So for instance, these guys would be what? Local minima, because they're the bottom of valleys. All right. So local minimum, we would say what? B and R. I'm going to just kind of do like this. Okay. So those are local minimum just because they're the bottom of valleys. But then if we want to identify the absolute minimum, if we would compare that to the endpoints, right? The endpoints are higher. So the overall lowest point, once we consider the endpoint, is going to be this guy here with R. So that would serve as our absolute minimum. Maybe I can just like duplicate that. So that would be our absolute minimum. Because when we compare the Y values, like for instance, like we have a Y value here, a Y value here, all of these, we consider all the Y values. This guy here is the lowest Y value. And again, we can only say it's the absolute minimum because we're given some endpoints, right? A and S are endpoints. So because we have those endpoints, then we could say, oh, well, this is the absolute minimum over that interval, over the interval from A to S, right? But without those endpoints, then we can say that these guys are local minimum, So when we say minimum, we're referring to like the value of Y, right? So like over here, what value of Y are each of these points given? Okay. So those are the minimum, and then maximum. So local max. For instance, this is going to be a local max. Honestly, this is the only local max, right? So for the locals, we're disregarding the endpoints. Yeah, it would be this guy. They might throw this in there, but that's usually discussion around the endpoints. That's usually with the absolute max. But this guy here is definitely a local max, right? Because it's the peak of a mountain. So then that would be C, local max. Okay. And then when we want to talk about absolute maximum, now we introduce the endpoints, right? So if we consider all of these points in addition to the endpoints, the absolute max, well, let's see, here's a local max, here's one endpoint and the second endpoint, and so the highest is going to be this guy here, right? That's the highest Y value. So that's going to be our absolute max at S. that's from the endpoint. And then neither a max nor a min. I think, D. Let me see. Are there any other points like D? A. Okay. I would say A and D. Right? This is an endpoint. It's neither a max nor a min. D is neither a max nor a min. I think it's just those two. So A and D, neither a max nor a min. In hindsight, it'd probably be better to just make those boxes bigger so I can just write directly in them. But that's how life goes. Okay. Let's see. I think that's it. Okay. So again, this question was just like a test on the definitions of the terms. When we kind of talk about it, we would do the local max and min first, and again, just local max and local min. Those are just, the local max is the peak of a mountain. Local min is the bottom of a valley. And then when you want to find absolute max or absolute min, you can only talk about that when you have on a closed interval, when you're given some endpoints. So then what you do is list out all the y values, for those max min along with the endpoints. And then whichever has the highest y value is your absolute max. Whichever has your lowest y value, and it might be more than one, is your absolute min, right? Okay. I can't think of anything else there. So with that, we're gonna end this question, and we'll be back momentarily for the second installment. See you in just a moment. All right, and we're back. Greetings, YouTube. Beautiful mind here. This is question 2 of a series of 3 homework questions from calculus. This question asks us to sketch the graph of f. Yeah, sketch the graph of f and use your sketch to find the absolute and local extrema of f. So what we have here, this is called a piecewise function, right? It's basically multiple functions on one graph, right? So this is like y equals 2x plus 2, and then this other one is like y equals 2 minus x. But so when we're going to graph this, we're going to graph each one like normal, but then we got to erase parts that we don't need. We have to restrict the first one only as x goes from 0 to 1. And then the second one we restrict it to as x goes from 1 to 3. And then, the biggest thing is you got to be sure to pay attention to these inequalities, because they determine if our endpoints are filled in or open, right? Okay. So let's graph this first guy, this y equals 2x plus 2. We're just going to graph it like normal. Okay. And then we're going to remove the parts that we don't need. And let's color code this. Let's do that guy. Let me find a color. All right, we'll do this dark blue here. Undo. I don't know how that got into it. Why is it capturing that? Okay, that looks fine. Yeah, I don't know why I was doing that. Anyway. Pen is hanging on for dear life. I gotta go to the shop. But anyway. Okay, and let's do the other one, the second one. We'll do it. I was thinking it's dark purple. Okay. No. Because I want more of a distinction. I was going to do like this green here. Okay. All right, that's fine. Okay. So 2x plus 2, right? So that's basically a line, right? It's the highest power on any variable is a 1. So that means we're dealing with the line. So that we can think of that in terms of y equals mx plus b, which is the slope-intercept form, right? So when we're graphing lines, maybe I should have, let me change the color because I don't have the other one ready to go. And that's probably going to change that, of course. I don't know why it's doing that. And I don't know why my voice just went so high. Anywho, okay. Okay, now we're in business. So y equals mx plus b. Our b in this case is a 2, that plus 2 on the end. So that means our y-intercept is 2. Okay, I'll just put a mark there. And then the slope, our rise over 1 is 2. The slope comes from, so our y-intercept came from this guy. Our slope comes from here, so the slope is 2, so that's up 2 and over 1. Okay, so if we go up 2, over 1, so 4 right here, right? And then you pretty much just kind of continue that pattern. We can get up to 6. Let's see. Up 2 and over 1, so 6 will be there. Let me see. And then we get a point here. So again, if we were graphing it like normal, I'm just going to connect these with a straight edge. All right, we'll get something along those lines. All right. So, but then it says that it's 2x plus 2 when x is greater than or equal to 0 but strictly less than 1, right? So we need to account for that. Where is my eraser tool? I'm going to do a partial. So this only applies as x goes from 0 to 1. So I'm going to cut this pretty much like, oh, did it cut it? Let me just undo. That's fine now. And as x goes to 1, cut that. So I'm going to get rid of any part of the graph that's outside of that interval, right? So I'm going to get rid of this part. Okay, that's fine. I'm going to leave that. I'm going to get rid of this. Okay. And then the last part for the first line. So when x is 0, it can be equal to that. So that gets a filled in circle. And then when x is 1, that's going to be an open circle. So what I'm going to do there, something like this. I'm going to shrink it down. It's going to behave like that. Let me shrink it down just a little bit more if I can. You know what? Let's go with this. Then let's go style, make that thinner, that we wanted to fill with this color. So now it's behaving the way that we like, okay? So the left endpoint was filled in, the right endpoint was an open circle, okay? So that's the first one. Again, we just graphed it like normal, removed the parts that we didn't need, and then those inequalities told us whether our circle was filled in or open. Okay, so the second part, the second line in green, that's also linear because the highest power on any variable is a 1. So that means we're dealing with a straight line. We can also use y equals mx plus b. We do need to reverse the order because, you know, the x needs to come first. So it's like we have negative x plus 2. So that plus 2 means our y-intercept is 2, and then it has a slope of negative 1. Right? Okay. So down 1 and over 1. The second point would be here. Down 1 and over 1. Another point here. Okay. This goes to 3. So then down 1 and over 1. Okay. And that's as far as we need to go. Okay. Notice that both those inequalities are filled in, so those are going to be solid circles, and so we're just going to connect this with a straight edge. Okay. And again, it's already solid circles. Okay. So, yeah, so piecewise functions, I guess I can get rid of those now. All right, so piecewise function is just multiple functions on one graph. You graph them like normal, but then you have to remove the parts that you don't need based on your domain restriction for each line, okay? So if this is the graph of f, so then the absolute extrema, right? Max and min. Um, okay. Highest point. So the absolute max. Do we have an absolute max? So usually if we're doing absolute max, it has to be a closed interval, right? But if we look at that blue, we don't have it's not a closed interval, right? So it looks like we don't have an absolute max if we're considering the interval from 0 to 3, because even though it's bound, you can always find a higher x value. So you're kind of using your imagination, right? As x approaches 1 coming from the left, those y values are always increasing. Even though it won't go above 4, it's bound by a y value of 4. But you can always find, like, if you pick a y value that's close to 4, you can always find a higher one, right? So this is like, because like you can, if you zoom in like Ant-Man, you're always like, if you think about like 3.9, well, actually you could find a number high, a higher y value. You could find 3.99. Is that the highest? Well, no. You can actually find 3.999. Is that the highest? Well, no. 3.49. Is that the highest? Well, no. You see what I'm saying? You can just keep going forever. So there should not be an absolute max, but it is bound. But yeah, there's not and again, because usually we do that on a closed interval, right? So absolute max, I would say none, or that's just yeah, I would say it does not exist in my expert opinion, right? Absolute min. Again, if we're considering this as x goes from 0 to 3, we do have an absolute minimum value that happens over here, right? The minimum value, this y value, what is this? -1. So if this is the lowest point, the corresponding y is -1. All right. So we get an absolute minimum value of -1. Okay. Local max and local min, those are usually like the peaks of valleys and the peaks of mountains and the bottom of valleys. So since we don't have any curves or anything like that, I would say none for both of those. Let me think. Yeah, I don't know. I mean, we definitely have an absolute min, local max, and local min. I feel like this might be a trick question. Let me think about it a little bit more. Because you could say no, because that's an endpoint, and that's supposed to be all nearby. But on the other side, you have points that go up. Yeah, I would go with none. This might not be right, but again, usually it's the peak of mountains and the bottom of valleys. So for these guys, I would say does not exist or none or something like that. So I'll just have to get some feedback to see if that's correct or not. Maybe I'll do a little digging. But when I look at it now, that's what I'm getting, okay? So with that, we'll end the session here. And from one beautiful mind to another, take care. Peace. And we'll be back in just a moment for the third installment of the series of 3. All right, and we're back. Greetings, YouTube, beautiful mind here. This is question 3 of a series of 3 from calculus. Let me see. It says the graph of a function g is shown. Okay. And then it says, which of the following verifies that G satisfies the hypothesis of the mean value theorem on the closed interval from 0 to 8? So let me pull up the mean value theorem really quickly. Okay. So this is from ChatGPT. It says, asked it, what is the mean value theorem in calculus? The mean value theorem is a fundamental result in calculus that connects the behavior of a function over an interval to its instantaneous rate of change. Okay. So the statement of the mean value theorem, the hypothesis, let f be a function that satisfies one, continuity on a closed interval AB, and then two, differentiability on the open interval AB. Then there exists a point C in that open interval such that f prime of C equals f of B, the difference quotient, right? F of B minus f of A over B minus A, right? Let me see a little bit more. So the mean value theorem says that for a smooth differentiable and continuous function, at some point between the endpoints, the instantaneous rate of change, which is the derivative, or your f prime of C, equals the average rate of change over the interval, the closed interval AB, right? So we have, like for instance, if we go back to our image, we have this curve and we have some endpoints. It looks like the endpoints is x goes from where 0 to 8. So then if we consider like the slope between those points, all right? If we were considering the slope of those here, let's do it this way instead. All right? So if we consider this line, all right, where we have the slope between these 2 points, then as long as this function is continuous and is continuous on a closed interval from A to B, and it's differentiable on the open interval from A to B, then there has to be some point C on the open interval from A to B. Open meaning, you know, we get infinitesimally close to those endpoints, but we don't reach them. Closed meaning not only do we get infinitesimally close to those endpoints, but we actually do include those endpoints. But because the function is continuous and differentiable on that, it's continuous on the closed interval and differentiable on the open interval, then there has to be some C such that it has to be some C in the open interval from A to B, such that the derivative at that value of C has to be equal to this slope here, right? So you can kind of guesstimate it like here, right? So if what's the value of that C? That C is approximately like 2, almost maybe a little bit more than 2, right? That's where this diagonal, right about there, that x value is approximately 2. But then there's another point. Let's see where else does the tangent line, right there, right? So then there's another point about here. All right, so this x value about here, let me see if that's 8, 7, so about 6.3, 6.4, something like that, right? So that's essentially the mean value theorem. And again, that's just based on those endpoints. So I just drew a straight line based on those endpoints, and then we can get a tangent line approximately there, and then another one approximately here. Okay. So then it says, which of the following verifies that G satisfies the hypothesis? So we got that one correct. G is continuous on the closed interval. G is differentiable on the open interval. Okay, so that's just the premise in order for us to use the mean value theorem. And then B asks us to estimate the values of C that satisfy the conclusion of the mean value theorem on the closed interval from 0 to 8. Right, so I think when we just did it a moment ago, we got about approximately 2 point something. So I'm just going to circle this guy here. And then I think we got 6 point something. I think the 6 is good. Right, we said about 6.4 or 6.5. So that's the change I would make there. And then C asks us to estimate the values of C that satisfy the conclusion of the mean value theorem on the closed interval from 2 to 6. So instead of doing it from 0 to 8, now we're going to do it from 2 to 6. So let's go back to our image. Okay. So from 2 to 6, let me see. 2, 3, 4, 5, 6. So from here to here. Okay. So that's the line that we're working with. So then we want to kind of move that around to see where we can get it to behave like a tangent line at a point. So about right there, that C value. So that's one of them. If there might be another one. I think there is. All right. So in reviewing my video, I noticed something. I think I did from 1 to 6 instead of 2 to 6. So I have to go back and augment that last one right here. So it says from where. So we need to augment that. So let's go here, get rid of this stuff, delete. Okay. So from 2 to 6. Let's see, 1, 2, 3, 4, 5, 6 is here. 2 is like here. Okay. All right. So now from 2 to 6, so we see it crosses about there. I mean, it creates a tangent line at about that point, and so that x value right about there, right about here, that corresponding x, 1, 2, 3, so like 3.5, and then it does it again over about here, and that corresponding x is 4, 5, about 5.5. So it looks like about 3.5 and 5.5. Okay. So I noticed that I think I did it from 6 to 1 initially, and that wasn't right. It was supposed to be from 2 to 6 instead of 1 to 6. Okay. So we got 3.5 and 5.5. Oh, how do we have the right thing? Yeah. Okay. Well, somehow I think that still got the same result. So okay, maybe yeah, I think we'll just kind of go with that. Okay. And I think yeah. Okay. And so yeah, that was it. So and with that, we'll end the session here. And now from one beautiful mind to another, take care. Peace.